Hello. So this video we are going to be talking about exponential functions in modeling, so the so-called exponential growth and decay. As a fair warning, you've probably seen this content before, and I'm going to do it in a way that is almost certainly radically different. And the reason why is because a lot of the time they teach sort of a number of different formulas. If you're thinking of like 1 plus r over n to the rt or something like this, or like e to the rt and like pert and all of these things, all of that is terrible. Don't need to know any of these things. And the reason why is because all growth, all exponential sort of model at this level at least, all of these things are the same in disguise. So there's really only one general format you need to know that covers all of these things: bacterial growth, half-life, interest rates, all of these things. Okay, so with that sort of warning out of the way, moving forward, let's go. So exponential growth. Personal pet peeve of mine, and this is one of those things that just sort of happens a lot. People will often use the term exponential growth, meaning that something grows really fast, right? And then they'll say like, oh, that's growing so fast, it's exponential growth. And it's fair that like exponential growth is very fast. In fact, it's so quick that really the human brain can't really wrap around how quick it is very well. But just because something's growing fast does not mean that it's necessarily growing exponentially. That's a very specific term. And again, in math, we're very precise with our language. So to be very clear, when we talk about exponential growth or exponential decay, this is growth or decay, where the amount of change each time depends on the current population. Okay, so if you have something that just sort of grows a lot every time, that's not exponential growth. If you have something that grows because it is like doubling or tripling or getting cut in half, if it's exponential, these are numbers that reflect the actual sort of amount that you're looking at, right? So as an example, if we have some bacteria, that bacteria doubles in size every 6 hours. Okay, so if we start with 10 cells, we want to know how many cells do we have after 3 days. Now, we know this is exponential growth, not because of how fast it's growing, but because we're using that word, right? Doubles, which means every 6 hours it increases, but the amount it increases depends on how much it has at that time, right? If it has 50 cells at some time, 6 hours later it'll have 100. But if it had 100, 6 hours later it'll have 200. So the amount it grew went from 50 to 100, right? The amount it grows changes every time because it's based on the amount you have. I know I'm beating a dead horse, but this is how you actually sort of distinguish between when you want to use some sort of exponential model versus any host of other things like polynomials or other things like that, okay? All right, so let's say we have this example. We don't know anything about exponential growth. We're just going to try to sort of figure this out as if somebody handed it to us cold and we don't know any of the sort of background math that we're working with here. How would you go about it? Well, a good sort of first step is to just sort of model the situation sort of at certain times right? So you might start by jotting down a table and saying, okay, I want to know sort of at certain hours, how many cells do I have for the things that I could sort of obviously figure out. If I wanted to know like at hour 3.278, I'm not going to know that without some sort of actual model. But at hour 0, right, when I start, I know I have 10 because that's given to me, right? And then I know after 6 hours, it doubles. So at hour 6, I'm going to have twice as many. I'm going to have 20, right? And then 6 more hours, 12 hours in, I'm going to have twice as many as that. So I'm going to go from 20 to 40. 18 hours, I'm going to have 80. 24 hours, I'm going to have 160, okay? So I can sort of start by making this table. And the goal here is not to just keep going until I get to 3 days. That would be a headache on many levels. One, the number is going to get very large and difficult to keep track of as I go because doubling is going to grow very quickly. But two, like that's very inefficient, right? Like I had to put in whatever it is, 5 rows for this one 24-hour period. At 3 days, I'm looking at 15 rows. If I needed to know after 30 days, I'm not doing that. Like 150 rows of this nonsense? No, right? The goal is to write out enough of the sort of lines, a big enough table that I can sort of figure out the pattern, right? Math is all about pattern recognition. So I'm going to look at this and say, okay, I have 1 day worth. I'm going to look at this and say, okay, I got, hour 0, 6, 12, 18, 24. At that time, I have 10, 20, 40, 80, 160, whatever. But now I'm going to start trying to hunt for a pattern. The way I'm going to do that is I'm going to look at, right, I already sort of clearly know the pattern for the hours. It just increases by 6 each time. But doubling is not a math statement, right? Like that's an English statement. I want to represent these cells, the number here, as some sort of expression, mathematical expression. So I'm going to start out by looking at this pattern and say, okay, 10 cells, that's really 1 times 10. And I sort of think of this way because I'm looking at each of these sort of numbers and they all have a 0 at the end. So I'm like, there's a common value of 10. 10 showed up as a sort of starting value. Maybe taking the 10 away will actually sort of help me narrow down what's going on in terms of like the underlying pattern between the steps. So I look at the next one. I'm like, okay, that's 2 times 10. Next one's 4 times 10, 8 times 10, 16 times 10. So I sort of took out that 10 because it was sort of in the starting information. And now I'm looking at what remains, what's left over of that. 1, 2, 4, 8, 16. But when I look at that, I'm like, these are all powers of 2, right? Like 1 is 2 to the 0. Like that one might throw me for a minute until I can figure that out. But 1 is 2 to the 0, 2 is 2 to the 1, 4, 2 squared, 2 cubed, 2 to the 4th. Now I have my pattern. My pattern is that every time I sort of do a doubling, whatever that is, right, every 6 hours, I have this power go up by 1. So now the goal is I have to sort of figure out the doubling statement, right? Because again, English, not math. So I still have this, what is a doubling, right? But every doubling, I now know that I'm going to increase this power of 2 by some amount. So now I'm like, okay, I want 3 days worth of information. So if I knew how many doublings happened in 3 days, I could sort of put that number as my power and directly compute, right? Because I could do, okay, if there's like 50 doublings, it would be 2 to the 50th times 10. That's what it would be, right? It's probably not 50 doublings, but like this is the idea is if I knew how many doublings I have, then I can figure it out. Okay, cool. How do I figure out how many doublings there are in 3 days? So we're going to use a technique here, which you may or may not have seen before, but is very useful in pretty much all of modeling. And you tend to very explicitly learn this thing in chemistry of all places, but it's actually, in my opinion, more useful in physics than chemistry. So this thing is called dimensional analysis. That's the fancy name. In practice, what it means is that you can sort of cross out units by sort of pretending that they are a common factor. That's sort of the hand-wavy explanation. So what I'm looking at here is I have 3 days, which I'm going to look at as a fraction, 3 days over 1, whatever. And I want to convert this to doublings, the term doublings. Now I know that doublings has to do with hours. So I need to convert my days to hours. So I can do that by multiplying by 1, but multiplying by 1 cleverly, right? Remember that saying? So I want to get rid of days and convert it to hours. And I know there's 24 hours in a day. Okay, so the idea here is that now this like days and day thing I can cross out, and now I'm down to a unit of hours. Moreover, I know that there is 1 doubling per 6 hours. So once I have sort of doublings as my sort of remaining units, I can verify by crossing out the common unit, right? So like days and day, that can be crossed out. Hours and hours, that can be crossed out. Now I'm down to just doublings and numbers, so I can compute. This tells me, right, if I multiply across, that I'm going to have 12 doublings, okay? So all of this work, and like for those of you shouting like, why am I doing it this way when I could just use a formula? We'll get to the formula bit first, but as promised, I'm trying to show you the process so that you can understand why no matter what situation you're in, exponential growth or decay, with a very tiny asterisk, because some situations like to use fancy vocab to mask stuff. We'll get into that later. But regardless of the sort of exponential growth decay type of model, it always works this way. It's always the same sort of process that underlies what we're going to do. So now we have 12 doublings, and what it tells me is that I can put in 12 doublings as my power of 2, and that gets me, right, I do 2 to the 12th times 10, and that gets me my 40,960, okay? And that's after 72 hours, which is 3 days. All right, so this is like I knew nothing going into this. I just sort of used mathematical reasoning each step of the way and tried to figure it out. But we don't want to do that every time, right? Because like this was not necessarily super hard, but it was not necessarily obvious and not easy the whole way through. So looking at this problem sort of again, if we're trying to do this as a sort of general exponential growth and decay model, we had this question, 10 cells we started with, double every 6 hours, how many after 3 days? We came up with the answer, 10 times 2 to the 12th, right? But let's look at what each of these numbers mean. That 10, that was the initial population. That's how many we had, right? The 10 cells. So really what this front number is, it's not just a 10 because it's a 10 because it's how many things we started with. If we started with 5 cells instead, we put a 5 there. The 2, well, that came from the fact that we're doubling, right? So every time we doubled, we increased the power of 2 by 1, but that's because we're multiplying by 2 every time. So again, this base is not just a 2 for reasons, right? It's 2 for a very specific reason, that we're doubling. If it were tripling, it would be a 3. If it were sort of increasing by a factor of 1.1, it would be 1.1, right? Last but not least is 12. Well, again, 12 was not pulled out of a hat, but it's a little less obvious because it didn't just come from the information directly, right? Like 10 was stated right there explicitly, and that's the initial population. Doubling, granted it's a word, but doubling, not a huge mental leap to get to 2, right? But 12 doesn't show up here anywhere. But again, remembering where we got that 12, the whole idea of it was that we really were tracking down how many times we sort of iterated, how many times we grew over the desired time period, right? We looked at, okay, we want to know after 3 days, and it grows in size every 6 hours. So if I have every 6 hours for 3 days, that's 12 cycles, right? It has sort of 4 cycles a day for 3 days. That's 12 cycles that it sort of iterates through. So again, the 12 is not just a mysterious number that pops out of nowhere. It's a little less obvious where it comes from, but it's just the number of growth cycles. Using these 3 things, we can just write down really any growth decay model ever. Like even the one with the asterisk follows this. It's just that the growth factor is very unclear because it's sort of hidden for reasons. But nonetheless, it still conforms to this idea. So anything that you're looking at, half-life, bacterial growth, interest rates, all of these things come down to this one sort of setup where you have however much you start with times however much it's growing each time. So like doubling, tripling, increasing by 1.1, whatever, to the power of however many times that you sort of are iterating it over your time period. So however many cycles occur over the time that you're interested in, okay? All of them boil down to this, which is why we're not going to go into all of the different formulas that you might have learned previously in this section because they are all this formula in disguise, okay? All right, so what do we do? Well, we talked about the sort of exponential growth / decay model. We went through it as if we knew nothing to sort of understand where it comes from and sort of understand what each of these sort of pieces ended up being with the initial population, the growth factor, and the number of cycles. Each of these things sort of comes out of the problem in a relatively natural, albeit not always obvious way. And with those 3 things, you can model any kind of exponential growth or decay, no matter what it is. So we sort of wrapped up with our abstract statement of this thing, the initial population times the growth factor to the number of cycles. And with that, we sort of cover all of the, at this level at least, exponential growth and decay modeling that you really are going to run into. Okay, so that is that.